Yeah, so going to collect your mini exams. If you have them, remember the plan is to have 8 of them, right? And you can choose to not turn in 2 of them, or I'll take your best 6. So if you have them, see, perfect. Stapled, name, perfect. That's what I'm looking for. Okay. Anybody else? Yes.
Well, did you just want the work and not the actual, like...
You don't have to turn in the exam.
Okay.
If just work is normally all I need. Anyone else? Okay. Here. Okay. Yes. Yeah, you're next. You turning in? No. Right across the hall. 316, 308. Right across the hall. All right, markers. Let's get this going. So I will get these graded as soon as I can. For sure within a week. I'll give them back to you within a week, but maybe even next time we meet. So any comments on the first mini exam? Was it more than you were expecting, less than you were expecting? Like, what's your feel for? Any opinions to start here?
It wasn't bad.
You didn't feel it was bad?
No, it wasn't bad. The ones we got done were bad.
I think that the big takeaway is what I already told you, which is don't wait on these things. I gave you the next one last class, right? Did anyone not get a copy? I don't know if I have a copy with me, but so you should be looking at that already. You should be trying to do some of the problems. Do not wait until a day or two before, because you will just run out of time. All right. Otherwise, this next one, you're not to work with anyone, right? So I do expect and hope that you will reach out to get help from me. I like to sit down. You know, it doesn't have to be in my office, but even if it's like over the phone, we talk about it. Texting. I want some dialogue to kind of get a feel. I do not expect you to be able to do it all without some help, all right? So if you're sitting there like, oh, I need to be able to do this and I don't like asking for help, like you need to kind of get that out of your mind, because in the real world, right, you work with your colleagues, you collaborate, you bounce ideas off each other, so that's kind of what I'm pushing for, is for you to get to that point where you're comfortable doing that. All right, we are going to move on. Last class, we had that very boring day where we were just looking at all these quadratic surfaces, right? Now we get back into business here. So we're going to start 10.7. We might even get into 10.8. And before you know it, we're going to be in chapter 11. So 10.7 is called Vector Functions and Space Curves. And I've added a note. This first note is not in the online notes. So I've added this 10.7.0, I called it. And I thought I'd start this discussion today with a question. Is a circle a function? What do you think? And in case you've forgotten or don't need a little reminder, the definition of a function back in college algebra is that a function is a rule which assigns to each element x in its domain exactly one element y or f of x in its range. So a function takes something in and spits exactly one thing out, right? What we can't have is taking in something and spitting out 2 different things, right? That violates what a function is. And so in this particular case where x goes in and we get one y that comes out, we would say, in this case, that y is a function of x. Okay, y depends on x, right? It is a function of x. And then what about the vertical line test? You remember the vertical line test? We use that for testing to see if something is a function. I try and stress this to my college algebra students. You know, when we're talking about functions, if I draw a circle, right, is that a function? Well, function of t, I'm not sure we've talked about that yet. right?
We use something like that in Cal 2, like near the end of it.
Parametric, exactly. Okay, so if we look at just back in college algebra, right, we would say that this fails to be a function of x. It fails to be a function of x because if you use the vertical line test, right, we hit it more than one time in certain places, right? In order to be a function of x, we can never hit it in more than one place when we draw a vertical line. And the idea here is that if I were to plug in a value of x, right, if I were to plug in some value of x here, then there would be two outputs, right? So x went in and there's actually two y values. I'll call it y1 and y2. There's two y values that correspond to that x value. And therefore, this fails to be a function of x, right? Fails to be a function of x. So in college algebra, all you look at are functions of x. That's it. That's all you're ever really worried about. In Cal 2, depending on your Cal 2, how far you got in the class, towards the end of the class, you may have studied what are called parametric functions. And in that case, we change our whole idea of this whole idea of like functions of x, functions of y, and we have this new independent variable called t. And from that, we can define, a circle as a function. That's what today is about. We're going to be talking about vector functions, which are functions. They still follow the same rule, right? One input, one output. But it's going to be different than what we've seen in the past, all right? Normally, all the functions we've ever seen in the past, you take a number in and you spit a number out. Or in Cal 2, maybe we took a number in and we spit out an ordered pair. Now what we're going to do is we're going to take a number in and we're going to spit out a vector. And that vector might be in two-dimensional space or three-dimensional space. And that's what a vector function is, all right? So here's the definition. Do I need to make this bigger? Can you all see this clearly? You sure? Okay. So a vector function, which we denote vector functions with this notation, r of t, all right? We've used that before, haven't we? We used it to define the vector equation of a line, right? So this is actually more broad, more general. We're saying vector functions in general are functions that are equal to, well, in two-dimensional space, it's just a vector, right, where you have f of t, which is what we call the first component function, and then the second component will have another function, g of t. So those are two independent functions of t. The independent variable here is t, right? So t gets plugged in, and then what comes out, once you plug in this t, you figure out what this is, you figure out what that is, and you create a vector out of it. Or if you're in three-dimensional space, it looks like this. R of t equals three components, right, into a vector. So you have your first component function, f of t, second component function, g of t, third component function, h of t. All right, so in all of these, the f, the g, and the h, those are all what we call real valued functions. They take numbers in. So this function right here takes a number in, spits a number out. This takes a number in, spits a number out. Number in, number out, number in, number out, number in, number out. Okay, this is called a vector function or a vector valued function. Any function that looks like one of those two. Again, like I just said, the domain of a vector function is a real number. So you plug in a number, and what you're going to get to come out are vectors, either in two-dimensional space or three-dimensional space. And this idea extends. You could have a vector in four-dimensional space, fifth-dimensional, sixth, seventh, eighth. We only go up to three-dimensional space here. All right, so some terminology, some language here. I've already used this. These functions in here are called the component functions, all right? The components, because with vectors, we don't call them, like when I write out a vector, like if I write this out, 2, 3 versus 2, 3, right? This is like an ordered pair. This is a vector. We call these components. We call these coordinates, right? These are the coordinates of a point. These are the components of the vector. So we call these component functions. Again, just language. All right, so what does the graph of a vector valued function look like? What does the graph look like? So if you start out, you plug in a number and it spits out vectors, what is this going to look like geometrically? For what we're doing in here, we're going to have curves curves or straight lines, okay? Curves or straight lines in 2 or 3 dimensional space. That's what you get. You don't get a surface, you don't get a solid, you get a curve in 2 or 3 dimensional space. That's when you have a vector function with one input, all right? Later on, we're going to have vector functions with 2 inputs. And our outputs are going to be vectors, and that's going to draw surfaces. But we're not there yet, okay? So right now, if there's one variable going in and a vector coming out the other side, then you're going to be drawing curves. Okay, so here's the first example that we're going to look at. And this is just some arbitrary example, all right? Let's look at the graph of r of t equals t squared. The first component function is t squared. The second component function is 1 minus t cubed. And so let's just take a look at this. It's in 2-dimensional space because it's 2 components. And let's just look at t values greater than or equal to 0. So let's just get some values of the function first. What would r evaluated at 0 be? A vector, right? That would be a vector. And what would it be? 0, 1. Okay, so I have the graph here. You can see it right now. T right now is 0. I know that's hard to see. That's 0. And do you see this red vector? That is the vector 0, 1. Do y'all agree? It doesn't go to the left or right. It goes up 1. That's 0, 1. Okay, let's plug in 1 now. So what happens when we plug in 1? You get 1, 0. So when I change this value to 1, I should get a vector pointed to the right. Okay? Now, there's an infinite number of values I could plug in. If I do like 1/2, right, we're going to get a vector in here. What would it be? 1/2 squared, 1/4. And then 1/2 cubed is 1/8. And then 1 minus 1/8 is 7/8. So that would be like to the right, 1/4, up 7/8. It would be the vector going like this, right? So we had the vector straight up, we've got that one, we've got that one. So you can see that if you start putting all these vectors together and just track the tip of the vectors, you're going to draw a curve, aren't you? And so that's what we're seeing here. We're seeing that if you vary the value of t, it draws all these vectors, right? The weird thing about vector functions is that vector functions create vectors, right? Just vectors. And then what we're doing is we're looking at the curve that is generated by the tips of those vectors. And so you get this thing that almost looks, well, it's not a parabola. We know it's not a parabola because the function, was the function parabolic? Only in the x-coordinate, right? Not in the y, sorry. Only in the x component was it quadratic. In the y component, it was cubic, right? But it kind of does look like the right side of a parabola. Any questions there? All right, next thing. Let's look at this one. And actually, you know what? Let's pause on this. Let's not do this one yet. Let's do something else first. Let's look at this one. I always assume my students know this one, so let's just try this first. Cosine t sine t. This is a really important vector function because what does it draw? It draws the unit circle, right? We can verify that by just picking some values. R of 0, where would we be? 1, 0. Okay, so let me draw that over here. That draws me the vector that, let's say this is 1. 1, 0 is the vector goes here to there, right? So we're kind of like talking about that point right there. And then I could plug in any value of t. Because these are trig functions, I'm going to plug in angles that we would know on the unit circle, like pi over 4, something like that. So if we do like pi over 4, you know, cosine and sine of pi over 4 are both the same, right? Root 2 over 2, root 2 over 2. And so that would give me the vector, let me see. I can already see I'm going to start to draw a circle, but that would be the vector here to here, right? All right. And so we continue doing this, right? We plug in maybe just one more. If we do r of pi over 2, we'll be at 0, 1. And that'll be the vector straight up, right? And then every value of t between 0 and pi over 2 is going to create the rest of that first quadrant, right? And as I let t get bigger, it's going to come around, right? It's going to come around, it's going to draw it. And then here's the part that's critical, I guess, in this. And that is, let's say we come around once and we come back, or no, let's get to this point right here, this vector right here. See, back when we were in college algebra, we would say that a circle is not a function, right? Because it fails the vertical line test. But do you all see here that this output and this output come from different inputs? They no longer come from the same x like we were in college algebra. These are coming from a t. T is almost like a clock running in the background. So what t value would give me that if I just went from here to there? What t value would I need to get to that? 7 pi over 4? And that would give me root 2 over 2, negative root 2 over 2. And see, these 2 points, right? I don't even worry about a vertical line anymore because these 2 points came from 2 different inputs, right? Came from this one and this one, right? In fact, what if I draw the circle again? What if I go around and I come back and I want to come to here and draw that point again? Is that going to violate being a function? I'm going to draw a point right on top of another point. Does that violate the function idea? Do they come from different inputs? Yes, right? What would be the angle if I went all the way around then to here? 9 pi over 4. See, 9 pi over 4, that would give you the vector root 2 over 2, root 2 over 2. Do y'all see what I'm saying? Because the inputs are all different, doesn't matter. We can go to the same output. Remember, a functions, college algebra, functions can look like this. You can go from here to here. You can't have that, right? That violates being a function. That's not a function back in college algebra. But you can have this, right? You can have 2 different inputs go to the same output. That's still a function. And that's kind of what's happening here with that point. We have 2 different inputs that go to the, wait, sorry, where is it? This one. 2 different inputs, right, that go to the same output. That's still okay in terms of being a function. So the beauty of well, one of the beautiful things about vector functions is that now we can draw curves in 2-dimensional space that overlap each other. We're not worried about the vertical line test anymore. We don't need to worry about any of that, right? At all, which is great. Because in the real world, imagine that every problem we ever faced in the real world required that we are dealing with a function that passes the vertical line test, right? Simple example I could think of is like, let's say I take a mouse, right? Let's say I have a little mouse here. I put him on the floor, I start letting him walk around, right? And we're looking at it from the top, right? I set him down, boom, I put him down, start the clock. He starts walking around the room, right? If I'm watching him from the top walk around the room, who knows what this mouse is going to do, right? Before you get to the idea of vector functions, this is not something we could deal with in Cal 1 or Cal 2 because Cal 1 and Cal 2 we're looking at functions, right? Y is a function of x. Now we're stepping out of that. We're saying, look, we can define this as a vector function, which means we should be able to do all the calculus that we learned before, but with this new type of function, all right? All right, so with that said, let's go to this example. I want to say one more thing. This draws me a unit circle, right? That draws me a unit circle. The radius of that circle is 1. How would I have to change that formula for the vector function? How would I change it if I wanted a circle of radius, let's say 5, instead of 1? Add a coefficient right out front, right? Add 5 here and 5 here. That would scale the entire unit circle out and it would make it a circle of radius 5, right? So generally speaking, if you have this, a cosine t, a sine t, like that, if you define a vector function this way, this will draw you a circle centered at the origin with a radius of a. Okay? That's what that draws. All right, now, with all that said, Let's now do this note. Let's look at this vector function. What do you see with this vector function first that's different than what we were just looking at? It's got a z component, right? Which means the curve that this draws lives in three-dimensional space, right? Okay, so what I'd like for you to do is first look at the first two components. That just draws me what? A circle, right? A flat circle in the xy plane, because these are the x and y components. So what's happening is if I'm thinking about this in three-dimensional space, if I'm looking at it from the top, it's just drawing me the unit circle, isn't it? That's all it's doing. But as we're drawing the unit circle, what's happening to the z component? It's t over 5, right? T over 5, what kind of function is that? Linear. It's linear, right? So as you're trying to draw this circle, remember this is the x-axis coming out at you there. This is the y. So if I draw my unit circle, I'm going to start 1 unit out here on the x-axis, and then I would be drawing like this around. That would be my unit circle. But as I do that, my z is doing what? Growing linearly. So I'm drawing, and as I draw, I'm starting to raise my pencil up as I draw the unit circle, right? And my z is coming up linearly. So what should this look like? Spiral spring, more like a spring. It's going to look more like a spring. See, looking at it from the top, now that's not directly from the top. We have a little bit of, I mean, if you were to go to infinity, it would look like a circle. If you were to be able to look from infinity, but if you understand? Yeah. Okay, all right. I can actually have the computer go to infinity and give us the circle, but as soon as I start moving it around, I lose that. So, all right, that's what it looks like from the top. And then from the side, you can see that, I think the easiest way to see it from the side is come in like this. This is linear growth right here. This is linear. Now, of course, it's curling back around, but it's linear growth as you go up. Make sense? What would happen if I change that? What happens if I change that function there instead of t over 5? What if I made it 5 times t? What would happen to that spring? It would be like more stretched out because it's growing faster, right? It'd still be a spring, but it would be stretched out. What if I did something like t squared? Really fast, right? That would be quadratic growth as you draw the spring, so it wouldn't be symmetric. Like right here, these the spaces between these like spring, right, are staying the same because it's linear. But if I change that z component to t squared, it would be, the space would start to increase between those. Okay, good? All right, so back in calculus, right? Think about what you learn in calculus. You talk about functions, right? And then in calculus 1, after you talk about functions, you then do limits of functions. After limits, you do continuity. After continuity, you do derivatives. After derivatives, you do integration. We're going to do all of that today, okay? We have a new function called a vector function. We're going to talk about the limits of those vector functions. We're going to talk about continuity of those vector functions. We're going to talk about what the derivatives are and then what the antiderivatives are, right? Okay, so first things with the limit, good news. I have great news, all right? If you have if you have a vector function, either in 2 or 3-dimensional space, then we define the limit as follows. So we write the limit just like we did in Cal 1. Limit, this time t is our variable, so t is approaching a of the vector function. What does it mean? Well, it means you're just going to take the limit of each of the component functions. That's it. So if you can do a limit in Cal 1, you can do a limit for vector functions because all you're doing is 2 separate limits for each of the components. Or if you're in 3-dimensional space, you'll do a limit for each of the 3 individual component functions. If those limits exist. Remember, limits don't always exist. So here we go. There's a problem like this on your next test, right? I believe. There's a limit problem. And in that limit problem, I'm going to check to see if you remember all the different things from limits from Cal 1, like L'Hopital's rule, things like that. So this problem is going to be, I think, a little bit easier than the one on your take-home, but the idea is the same. All right, so we want to find the limit as t goes to 0 of this. So if we want to find the limit as t goes to 0 of r of t, then what we need to do is we need to figure out what this vector function is as we take the limit as t goes to 0 of all three components. So we have three limits to calculate here. Isn't that nice? You just do each one separately? Yeah. That's the definition of the limit of a vector function. So let's see how easy these are for you. What's the limit as t goes to 0 of cosine of t? Well, you first try what we call direct substitution. Just plug 0 in. Cosine of 0, 1. Okay, there's no problems there at all, right? So this is just giving me 1, okay, comma. All right, now let's try the second limit. T goes to 0. Sine of 0 is 0 over 0. 0 over 0 is an indeterminate form in Cal 1. And depending on what you learned, when we get 0 over 0, right, this has the form 0 over 0. There's two ways to do this problem. First way is that you remember this was one of the foundational first limits you ever learned in Cal 1 where they tell you, look, you just got to remember the answer to this is 1. And then later on we say, oh, but if you use L'Hopital's rule, you can figure this out. I'm going to use L'Hopital's rule right now. So show of hands real quick. How many of you know what I'm talking about when I say L'Hopital? Yes? Because I know some. Yes? You don't know L'Hopital? It's okay if you haven't, but we got to fill that gap in. So if you might need to get with me on it if what I do looks totally familiar. I mean, unfamiliar to you. So because this is going to require L'Hopital's rule, what I'm going to do is I'm going to do some scratch work on the side here. Even though this is not a very hard problem to do, I'm just going to come over here and I'm going to do this limit on its own. Limit t goes to 0, sine t over t. Okay, because I have 0 over 0, that's what I need for L'Hopital's rule. L'Hopital's rule says that this will be equal to, and then you have to indicate somehow that you're using L'Hopital's rule. You can either put an h here, you can put an h with a circle, you can put an L here, or you can put an L with a circle. Just somehow you need to let people know you're about to use L'Hopital's rule. All right, I use an L with a circle. And then what you do, what is it? What's the rule say? If you have 0 over 0, you take derivative of top and bottom separately, right? Independent of one another. Derivative of sine is cosine, derivative of t is 1. You're just taking derivative of top and bottom separately. No quotient rule, right? Don't do anything like that. And now just evaluate that new limit. And this answer, cosine of 0 is 1, 1 over 1 is 1, so you get 1. So this answer is 1. On your next mini exam, you need to do these limits by hand. Just an answer, a correct answer is not okay. You've got to show how you got the limits, all right? All right, we good on that so far? Okay, what about this one? Oh, wait, you can use L'Hopital when you have 0 over 0 or what? Infinity over infinity. And it doesn't matter if it's negative infinity over infinity or positive infinity over negative infinity or negative over negative. If you got infinities on top and bottom, you can use L'Hopital. Or 0 over 0. Or what? No, 1 over infinity would go to 0. If your numerator's headed to 1 and your denominator's getting huge, then that ratio will go to 0. All right, good. Let's see what's happening here. T goes to 0. E to the 0 is 1. 1 minus 1 is 0. So we're getting 0 on top there. On the bottom, we're getting, well, t is going 0. So we get 0 over 0. Okay, I can use L'Hopital. All right, I'm going to do it again over here on the side. So this is e to the t minus 1 over t. Okay, I'm going to use L'Hopital's rule. Derivative of the top. What's derivative of e to the t minus 1? Just e to the t. Yeah. And then over derivative of t, 1. Okay, now let t go to 0 again. You get 1. Okay, we get 1. We get the vector 1, 1, 1. Right? So what is this saying? I mean, we need to understand what this is saying. Let me try and illustrate this with an example. Let's think back to Cal 1, college algebra, however you want to look at this. When you look at that function right now, if I were to, so I'm asking you to consider what's happening here by first looking at this. If I asked you right now what's f of 2 here, what would you tell me? What's this function evaluated at 2?
Undefined.
Undefined. It's undefined. You can't plug 2 into this, okay? This is undefined. Now, can you tell me what's happening? What's the limit? Let me erase this right here. Can you tell me what the limit is as x approaches 2 of this function? Can you tell me what happens as we approach 2? Well, as you approach 2, what happens here? You get 0 over 0, right? So you could use L'Hopital if you wanted to. You're going to get an answer of 2. You could also do difference of squares, cancel out factors, but you should get an answer of 2 here. Wait, hold on. It's not 2. It's 4. I apologize. It's 4. Should be 4. Okay? Yes?
Why would it be undefined? I thought it was only undefined if you had a number on top and 0 on the bottom. If you plug in 2, wouldn't you just get 0 over 0?
Which is undefined. 0 over 0 is undefined. The limit is defined. Like the limit exists, but the function evaluated there does not exist. So this is undefined. See, one of the big problems, and I actually was just doing this in my 1414 class last week. We were doing this problem, something like this, and we factored the top. We factored the top like this. I'm talking about this right here. We were looking at that. No, forget the limit. We were looking at that, and then my students did this. And I said, that's fine, but when you do that, right, when you do that, there's a little fine print down here. You know, like when you're reading a contract and you just accept all, right? Okay, you don't read all that fine print. There's fine print right here. You can only algebraically cancel that if you promise me x is never 2. There's a fine print there. When we cancel factors in an algebraic expression, we always have to exclude the possibility that those factors could ever be 0. So this algebraically is equivalent to x plus 2 so long as you're not letting x be 2. If you're going to let x be 2, it's undefined. So when you draw this, okay, if you draw this, if you go to Desmos right now and you graph this function, here's what it'll look like. It'll look like this. It'll look like a line. Actually, let's do it. It's right frickin' here next to me. Okay, let's just do it. Because this is a subtle but very important point. There's a hole, okay, but let's see if Desmos actually gives me the hole. So I'm going to type in x squared minus 4 over x minus 2. Okay, that's what Desmos gives me. Can you all see that? Okay, what's the value of this function at 2? What does it appear to be according to Desmos? It appears to be 4, right? But if I just click on the function and drag, it gives me the ordered pair, right? At 0, it should be 2. At 1, it should be 3. Agreed? And then when I get to 2, it should be undefined, right? And it still baffles my mind why, at this point, 2023, here we are, that Desmos is not smart enough to put a hole there, right? I mean, it does a lot of things. Why can't it identify where it's undefined?